All right. Good morning, everybody. Can you hear me?
Yes.
Okay. Again, just to confirm, the class is on Zoom. The polls are going to be on Zoom. So there will be no Piazza votes, right? All right. Let's begin. What was the last topic we were discussing, guys? Anybody? What was the last topic we were discussing? CNNs, right? We ran through the whole gamut of everything to everything CNN, what CNNs are, how to train them, different variants, and so on. We begin our new series on recurrent neural networks. So, what are recurrent neural networks? Now, there are many situations where one must consider a series of inputs to produce an output, where the output too may be a series. So, here are some examples, like speech recognition. Now, if you were performing something like a keyword recognizer or an isolated word recognizer, wake up word recognizer, you would pass segments of audio to your system, and the system must analyze the entire recording to decide what was spoken in it. So, if you wanted to recognize "Hey Siri," it has to see the entire recording, and having seen the entire recording, it then decides whether "Hey Siri" was spoken or not. So the input is a sequence of vectors, the output is a classification result. Or something like this, text analysis. This is one of my more favorite, less favorite examples, being a Steelers fan. The Steelers, meanwhile, continue to struggle to make stops on defense. They have allowed, on average, 30 points a game and have shown no signs of improving anytime soon. So is there anything in this text that tells you which sport they're speaking of? Can you identify anything here that tells you which sport they're speaking of? Yes, no. So, okay, so how do you decide that, what sport they're speaking of over here? If you had to guess, the team, so the Steelers, 30 points a game, contextual knowledge. So again, you'd have to analyze the entire sentence before you decided whether it was football or basketball that was being discussed. Or same thing, if you were doing something like analyzing the stock market, then you would want to look at the sequence of stocks and the stock values over the past several days to decide which stocks you want to invest on today. So the inputs now, here, the input is come on. Here, the input is a sequence of words that has to be analyzed before you come up with a conclusion. Here, inputs would be sequences of vectors, where the vectors are vectors of maybe stock values. And at each time, the output could be a scalar. Should I invest in a particular stock or not? Or a vector, predictions about a whole bunch of stocks. And this decision must be taken considering how things have fared over time. So in each case, you're considering a sequence of input vectors, to produce one or more outputs, where the output may be produced either at the end of the sequence or after each sample. For example, here, you would be making predictions every single day. So you're analyzing time series to make predictions. And this can obviously be done with neural networks. So before that clear what we're talking about? Yes, no?
Yes.
Okay. Be a bit prompt, guys. Can I actually see a few yeses on the chat box so I know I can proceed, right? So a representation shortcut. Typically, when we've drawn neural networks like this figure to the right. When I've shown an input, I've shown a series of balls or squares indicating all the components of the input. When I've shown a layer, I've shown all of the neurons in the layer and so on. But then this is a bit too verbose. If I were to rotate this network, this picture out on the side, it's going to look like this, where this box here represents this vector here. This box over here represents this layer of neurons. This box represents this layer of neurons, and so on. And the arrow represents a full connection between the input, between all the elements of the input and all the elements of the output. So also, if I were to if I were to make the first hidden layer look at two vectors, then the corresponding representation would look like the figure to the right over here, this one, where now I also have a second vector, right? And if I were to add yet another layer out here, then the figure is going to look like this, where this box represents this layer. So when you see a picture of this kind, you must assume that each box actually represents an entire layer which is fully connected to the previous layer. Is this picture clear to everybody? This illustration? Yes or no? Yeah. Okay, good. So, all right, let's continue. So now here's the stock prediction problem. You must consider the series of stock values in the past. And now if you want to decide whether you want to make an investment on this day, would you just be considering what happened today, or would you also be considering things that happened in the past? Would you be looking at trends? What would you do? Anyone? Both, right? So what kind of a model would look at today and some of the past? What kind of model have you seen so far that could do it? Anyone?
A time series model.
A CNN, right? So, which is something like this. You're going to have, again, remember each box represents a vector of inputs or a complete layer of neurons, right? So this, if you wanted to make a prediction based on the past several days, then you would consider the stock values today, the day before, the previous day, the day before that, and the day before that maybe, and then use all of these to make your predictions. So on every single day, you'd be doing just this, and this is a model that you're all familiar with. This is what kind of a model is this? Anyone? That's a 1D CNN, right? So the
excuse me,
problem with this is that, so a time delay neural network or a 1D CNN. This is a finite response system. Something that happens today only affects the predictions of the system for the next n days into the future, where n is the width of the system. So somebody has a question. What was the question? Okay. So
yes,
let's
sir.
look at it.
Sir.
Yeah.
Sorry, sir.
Go ahead.
My question is that basically, does like the 1D CNN framing kind of like imply that the stock prediction like only like depends on like the number of predictions within a window of like a time frame?
Exactly, right. And so this has the consequence that something that happens today, say on the day indicated by this bright red box, will only influence predictions for a short period of time afterwards. So as your CNN scans to the input, the orange input influences y of t. It also influences y of t plus 1, t plus 2, t plus 3. And then when you get to t plus 4, the orange box no longer has any influence. And so this is a finite response system. Something that happens now only influences the outputs for a finite period of time after the input. Now, when you have a finite response system, then you must consider how much of the past do you want to consider. For example, if I'm making stock predictions, I want to go back and look at trends over time. So if I want to look at a longer period of time, what I would have to do is to look at more of the input in this manner. This makes the network more complex, but then no worries, we have CPU, we have memory, we can do this, right? But then you have this issue. How much of the past must we be looking at? Now, here is a typical stock market index for over time. And you're going to see all kinds of trends. You're going to see weekly trends. People buy more on Mondays or Fridays, right? You're going to see monthly trends. There's a lot more purchasing happening at the end of the month when people get their paychecks. You get seasonal trends because at the end of every season, all the stores offload their latest stock and get stock for the next season. And then you have annual trends. Purchases jump up every Thanksgiving and every Christmas. And so you'd have to look back over a full year to know that, it's Christmas time, maybe the stock market is going to jump up. But it's not sufficient to look over only 365 days. You'd have to see this over a much longer period of time to actually realize that there's an annual trend over here. And so you're going to need something of this kind where you're looking way back into the past. In fact, if you want to capture all trends, you want an infinite response system where any prediction is made looking at everything that happened in the past to the beginning of time. And so conversely, something that happens today in the system can continue to affect the predictions of the system forever, possibly with weaker and weaker influence as time passes, but it will continue to influence your predictions forever. And that's the kind of model we are really looking for. So what kind of model would do this? Okay, is this clear, what I've said so far? Yes, no? I'm waiting for a response, guys. Can you guys hear me? Or is it? I can't see anyway. Can you hear me?
Yes.
Okay.
Yes.
So please do respond because I will wait. Okay. I need to see a few yeses. I'm also on the end of a not too great internet line. And so if you don't respond, I'm also likely to think that maybe my network is just parked. So do me a favor. Anyway, so we want infinite memory, right? And an infinite memory system is going to be something that's different from a CNN. So for this, here is our first poll. Can you see the poll?
Yes.
Yes.
Seconds, guys. All right. So let's stop this right here. And okay. Now, the first question, true or false? CNNs are finite response systems. True or false? Right.
True.
So second statement, an input that at time t affects the output of the CNN for all time, true or false? This is false, right? Because if the CNN has a finite window, once your kernel slides past the current input, that input is not going to influence predictions, the subsequent predictions. And so a CNN is a finite response system. And so the first statement is true and the second is false. What we want is an infinite response system. Something that happens now should influence predictions forever. And what kind of system would do that? Here's one. Here's one where the output at any time, yt, is a function not just of the current input, but also the output at the previous time. So this means that, of course, you'd have to define y of -1 to make predictions at t equals 0. But then an input at t equals 0 is going to produce y0. But then y0 is going to produce y1 because y0 goes in here. And then y1 goes in here and produces y2 and so on. So even if the remaining inputs are all 0, there are no further inputs, the network is going to continue producing outputs forever. So a single input influences the output for the rest of time. This particular form of network is what's called a NARX network, or a nonlinear autoregressive network with exogenous inputs. The model has been out about for a long time. and it's actually become a little more popular recently. So here, the history, the information about the entire past, where does it lie? Is it part of the model or is it in the output itself? Where is the information about the past? Anyone?
The output itself.
The output itself, right? So here's what happens. At time t, you make a prediction by t. Then at the next time, to make your prediction, you consider the current input and the past output. At each time, you're actually taking in the current input and the past output to make your predictions. Now, here's the complete chain of prediction, dependencies, and you can see how something that happens here keeps influencing the output forever. So a single input at any time is going to influence the outputs for the rest of time, forever. I'm going to simplify this box figure without showing this yellow box and draw it like so. It just says that the output from the output layer is both seen and fed to the next time. This is just simplifying the figure. But then the figure conveys the idea, right? Something at any time is going to influence the output forever. Now, this is what is called a first order NARX network, where the output at any time depends only on the current input and the immediately past output, but you can generalize this. You can say that at any time, you're looking at a window of inputs and a window of past outputs. This is just a generalization of the simpler network. Nonetheless, the fact remains that the memory of what has happened so far is entirely buried in the output of the network. There's nothing stored in the intermediate variables of the network that tells you what has happened so far. This making sense to everybody? Okay. So these NARX networks are very popular for time series prediction. They're used for weather prediction. They're used in stock market prediction. They're used in tracking systems. Lately, all your autoregressive language models are essentially in some form or the other NARX networks. Any phenomenon that has a distinct innovation that drives an output, a time series that drives a time series, can be modeled using a NARX network. And the key thing here is that the memory of the past is not in the network. It's not in any of the intermediate variables of the network. It's in the output of the network. So let's make the memory more explicit. I'd like to have something inside the network that retains memory. This kind of makes sense, right? So you want a state in the network so that you can carry that state over to future computations. And one simple way to do this, what people first did was to include an explicit memory variable whose job it was to remember. So the memory at any time is a function of the past outputs, any hidden states at this in the past, and also past memories. Then the hidden state at any time is a function of the current input and whatever the network remembers, and the output depends only on the hidden state. This is the general nature of the network. And a couple of different examples were proposed early on. So here's the earliest one. This was by Professor Michael Jordan, who is now at Berkeley, but used to be at MIT earlier. This was his PhD work in the late 80s. This was, I think, the first real model to include an explicit element for memory in the network. But then it's kind of naive. Now, what happens over here in this network is that the entire memory is just embedded in the most recent output. So this kind of maybe shortchanges you a bit because the most recent output is a discrete phenomenon. And so what the Jordan network did was to have a memory unit that maintained a running average of past outputs at any time. What was in the memory unit was the most recent output plus some mu times the past memory. Once again, observe that the memory unit is still only capturing information in terms of what the network has already output and not in terms of any of the hidden states of the network. So the memory has a fixed structure. It doesn't learn to remember. We just sort of force this little box that maintains a running average of past outputs, and this is the memory. This was the Jordan network. This model clear? What's happening here, guys? Yes, no? Okay. So clearly this is not great. So let's take a step forward. Let's actually look into the hidden states of the network. That gave us the Elman network. In the Elman network, the hidden state of the network at any time was cloned, and this actually fed the network at the next time. So at any time, the input to the network was the actual input and the hidden state at the previous time, except the hidden state was cloned. So this, because you're always reading the past hidden state, there's actually a recurrence. This hidden state stores state information about what happened in the network. And so it stores memory. But the way this particular network was trained, at any time when you perform back propagation, you would maybe get some divergence here. The derivatives would go back this way, and they could be pushed back even this way to update these weights. But then they were blocked right here because these two were not the same thing. They were just clones. So it's like having a second input to the network that's being fed along with this guy. And so derivatives were not propagated backwards from here. During back propagation, at each time, the derivative just did this separately. And so this was what was called a partially recurrent network. During the forward pass, the information keeps getting carried over time. During the backward pass, at each time, the derivatives stop at the most recent memory. Now, this is a problem because if you see an error over here, that error could have been triggered by something that happened here, which just got delayed and eventually caused an error. This back propagation, by stopping it right here, doesn't actually account for the fact that the error might have accumulated over time. And so, in some sense, it's less effective than it could be. Still, it does have the a characteristic that something that happens at some time continues to influence the outputs for all time. So this was a partially recurrent network. This making sense to you guys? What we saw here? Okay. And so the story so far in time series analysis, models must look at past inputs along with the current input. Looking at a finite horizon of past inputs gives us a convolutional network. Looking into the infinite past requires recursion. NARX networks recurs by feeding back the output to the input and then feed back a finite horizon of outputs. Then you have these, or not partial, but simple recurrent networks. Jordan networks maintain a running average of outputs in a memory unit. Elman networks store hidden unit values for one time instant in what was called a context unit. This was called a context unit. And these are simple or partially recurrent because during learning, the current error does not actually propagate to the past. They are blocked at the memory units in Jordan networks and at the context unit in Elman networks. So any questions? So Shuvay, when going forward, the hidden state is cloned. So in effect, in the forward pass, there is actual recurrence. It's just that in the backward pass, the derivatives just go this way and stop right here. Now, you might think of something that has to actually go over 2 time steps to trigger an error. So this guy would not trigger an error over here. So the fact that this had to go through 2 time steps to trigger an error doesn't get captured when the back propagation stops right here at each time. So that is the issue. But otherwise, during the forward pass, because the information keeps getting cloned, this context state actually carries information about the infinite past. That answer your question? Yeah.
I also have a question, Prof.
Yeah. Go ahead.
So basically, like, you're saying that the reason why it can't be like backpropped through the reason why networks can only be partially backpropped is because like here like it has to like get cloned like twice, but like in the backprop, like there's only like the ingredient doesn't really change. It doesn't reflect the fact that it was cloned twice, right? So I
So
think
it's only cloned. So the point is it's cloned once. But
Yeah.
basically during backpropagation, you keep chopping the network up and treat this as a mini batch where each instance is different. Right. So that's the issue here. Abhishek, so the point is you want the output is a very impoverished representation of the entire past. By having the network maintain its maintain memory in the internal state, the memory can be much richer, right? So Sumit will get to that, right? And so here is your second poll. You can take a look at the poll while I'm releasing it. Wait, why am I unable to launch it? Guys, TAs, can we actually launch the second poll? Yeah. For some reason, I'm not able to launch this poll. Yeah. Can you guys see the poll? Yeah. So, Shubha, in the original Elman network, there was just one hidden layer. But yeah, if you had multiple hidden layers, you could just you'd be cloning each of them. So Daniela, the output is just typically a single prediction, right? The hidden state is a high dimensional representation with a lot more information in it. So for example, if I'm predicting a class, then it says potato and that's it, right? How much information does that really contain? That's the issue over here. So let me stop this poll, and here are the results that you got. Let me stop sharing and okay. So first question, true or false? False. Okay, and what about the second one? True, right? So I'm not sure why some got that wrong. Okay. Now, so what we really want is something where you can also carry information backwards, propagate errors backwards. And this is important because sometimes or very often your information accumulates over time and then eventually something trips and it causes the output to change. And this is what makes time series, right? So it's not just a sequence of short memory events. And so you want to capture this phenomenon. So and that is already sort of here in this model. If instead of cloning the state, we directly connected this guy to this one, we could propagate the error backward. That gives us what is called a state space model. In the state space model, the hidden state is a function of the current input and the hidden state at past times. And the current output is just a function of the hidden state. So HT now is the state of the network. It summarizes information about the entire past. Of course, in order to be able to run this, you have to define h of -1 so that you can compute h of 0. And because there's no cloning or there's no external unit like a memory unit, you can see that HT directly depends on H0. And so this is a fully recurrent network going both forward and backward, or simply it's just called a recurrent neural network. So here's how the network looks. Here's the basic network. At each time, the hidden state is computed from the current input and the hidden state at the previous time. And the output is computed from the current input, current hidden state. So you have to define h of -1. And here's the complete computation. At time 0, you use h of -1 and x0 to produce y0. At time 1, you use h0 and x of 1 to produce y of 1, and so on. So again, you can see that something that happens here, if you just follow the chain of influences, it's going to affect the output for all future time instants. Now, although I've just drawn a simple green box over here, this box can be arbitrarily complex. So it could have, in fact, several layers in it. And so these boxes over here can actually be very complex. And they could, for instance, have 2 layers, in which case you'd be defining hf minus 1 for both. And then you can have all kinds of arbitrary connections of this kind. And it's still, nonetheless, this whole box, you can just view this entire green area as one box, which carries the network state and can be propagated forward. Shrikant, yes, you're going to be storing all of this information going forward. But that is the whole point, right? I mean, you don't need to during inference. You would need to during back propagation. The whole point of having this guy, which represents the state of the network captured over time, means that I don't need to see any of this at any given time because all of that information is encapsulated in this one hidden state, and that can be propagated forward. So during inference, it's actually very efficient. We have to store all of these only for back propagation, but that's always the case for training. That answer your question, Shrikant? So I'm assuming yes.
Yes.
Okay. And yeah, here's a more complex hidden state. But then in any case, the point is that an input at time 0 affects the outputs forever. Now this shows a system where the hidden state at any time is only looking at the hidden state at the previous time, but then you can actually have deeper recurrences, like something over here, where the hidden state at some time looks not just at the hidden state at the previous time, but also maybe at the hidden state 2 times time instance earlier, or 3 time instance earlier. Now, the only thing with this is that now we are going to have to define the initial values for these hidden states for multiple time instants. And once we do this, you can have deeper recurrences. But more generally, we just sort of use this kind of a simple structure where we look back one time instant, and the hidden state itself generally tends to be simply layered, right? So questions? Any questions so far? Yes, no? No questions, okay. So when these things are drawn, historically they'd be drawn like this. This was a recurrent network, right? So the recurrent, and you'd have this looping arrow. It didn't mean that the output over here went right back into this box. It meant that this was actually a recurrence over time. So a network of this kind with 2 loops means that you have recurrence over both the hidden states. Or something over here where you have recurrence over the hidden states, but also skip connections going upwards. The loops imply recurrence. So this network over here would actually be a computation of the kind shown at the bottom, right? So Shuei, this one, yes, but it's not. This one does carry information about this guy, but having explicit connections more than one step backward gives you higher order models. Now, if I were in class, I could actually draw things on the board. If you can hold on to that question till the end of the class, if I have time, I will explain it. Okay? So, but you can get more modes. So anyway, here's a more detailed version of this simplified model. This is just recurrence over a single hidden layer. This is recurrence over 2 hidden layers. Here's a recurrence over 2 hidden layers and skip connections. So do you understand how this figure works over here? Yes, no? Yes or no, guys? It's either a yes or a no. Okay. And so one thing you should observe over here is that when looked at in this manner, this is actually one giant network. You can think of these things almost as, unrolling over time. And it's a giant network with shared parameters because every column is identical to every other column. So I could just draw, I could draw my input like this. and say, I can draw my something over here. This is my first output. Then this guy goes here, and this is my second output. This guy goes here, and this is my third output, and so on. I could draw something ugly and lay it all out on the side. And so this actually ends up being a very deep network going this way. Does that even make sense? I'm assuming. So if you just lay the figure up on the side, it's actually a very deep network. So again, Ron, just think of it this way. I can have my inputs like so, right? And I'm assuming only one hidden layer. I can have my network like so, okay? And you have this guy, right? And now this is the next input. So basically, you're getting inputs going into every layer of the network. So this is actually just a very deep network, right? And this is something that we have to remember by the time we get to the end of the class. We're going to see why, okay? So which parameters are shared exactly? The parameters in this column are exactly the same as the parameters in this column, are exactly the same as the parameters in this column. And the red circle is a recurrent layer. Did I answer your question, Matt? Okay. And so let's continue. So how is the computation done? Fairly straightforward. Let's look at this at any time. At any time, you first compute an affine function of the input and the hidden state at the previous layer. Within the hidden state box, you compute an affine function of the input and the hidden state at the previous layer. So you have two sets of weights. One is the set of weights which correspond to this connection. I'm going to call them the current weights. And you have the second set of weights which correspond to this connection. I'm going to call them the recurrent weights, as indicated by the double index over here. And then once you compute this affine function, you apply an activation function to it. That's for the hidden state. For the output, of course, you just compute an affine function of the hidden state and then apply an activation function to it. So the computation is fairly straightforward. Yes, Jeffrey?
So the idea, sir, is that basically, like at each time step, like you're using the same W that you used in the previous time step on like the input at that time step, and using the same W used at like other time steps on like the previous hidden state for that time step.
That's right. And so that's why it's a shared parameter network, right? So you can see that these are my current weights. They correspond to this connection at the two inputs at the same time. These are the recurrent weights. The recurrent weights are referring to the connections over the recurrent edges. If I have a network of this kind with two layers in the hidden state, then for the first layer, I'm first going to compute an affine function of the input and the first layer hidden state at the previous time. So I have two weights. These are the current weights, and these are the recurrent weights. Then, of course, you apply an activation to it. For the second layer, I'd be computing an affine function of the hidden state at the same time, and the hidden state in the previous layer at the same time, and the same hidden state in the previous time. So again, you have two sets of weights. One is the set of current weights corresponding to this connection, and the recurrent weights corresponding to this connection. And the output, of course, is just going to be an affine, an activation applied to an affine function of the topmost hidden state. So are these computations making sense to you guys? Yes or no? What about the rest of you guys? Right? So very simple. There's nothing particularly complicated about any of this. And so if I have something of this kind, that would depend on the weights. And we'll discuss that in a couple of lectures coming, right? In the next lecture, in fact. So Same thing over here. They're going to have current weights, recurrent weights, and I have weights corresponding to the skip connections. So we've seen how we can analyze time series, and they can have many variants on the using recurrence, and we can have many variants on recurrence. A conventional MLP is a figure of this kind. I've obtained these images from Andre Karpathy from his webpage. So Hajar, yes, these are going to be very thick. They cannot really be parallelized, and that is a problem, right? So this is an MLP, right? I just have information going up vertically. There's nothing coming across time. But then here's a recurrence where a single input generates an entire series of outputs. That's a recurrent network. Here's another recurrence where I analyze it. So what would be an example of this? Like image captioning. I give you an image, I generate an entire sequence of words. Or here's one where I look at an entire sequence of inputs and generate a single output, like classification or determining if this was football or basketball. I analyze the entire text and make a prediction, right? You can also have this delayed sequence to sequence where you analyze an entire input sequence, and once the entire input sequence has been analyzed, you generate the entire output sequence. So this you could use, for example, in machine translation. You'd analyze the entire English and then generate the French. Or this is a model which sort of captures all of the others in some sense. This is a sequence to sequence where at each time you obtain an input and a recurrent input and generate an output. So there is an output corresponding to each input, and there's a one-to-one synchrony between the output and the input. So this you might use, for example, in stock prediction. Every day you're going to predict stocks. Or if you're analyzing text and determining the part of speech of the text, you'd have to do this for every word. So this is a simple recurrent network, but in fact, as we will see, all the other models, we try to reduce all the other models to this model to get our computations done. Questions?
I have a question, sir.
Mm-hmm.
So basically, we reduce the one on the left to the one on the right by like masking out like the outputs and inputs that we like don't use.
So if you have a time series, you don't really have the inputs to the right. So who's A. Fadia? I don't know your name, but yes. For the recurrent networks, I'm not sure that there's any backing in neuroscience, unlike CNNs where there definitely is. Right. At this point, it's a purely computational mechanism, at least to the best of my knowledge. There might have been work trying to show that there's some recurrence happening in the brain, but not, I'm just guessing, yeah. So the story so far, time series, thanks Ayush. So time series analysis must consider past inputs along with the current input. Looking into the infinite past requires recursion. We saw that NARX networks achieve this by feeding back the output to the input. Simple recurrent networks maintain a separate memory or context unit to retain some information about the past. But during learning, the current error doesn't influence the past. State space models retain input from about the past through recurrent hidden states. These are fully recurrent networks. And they need you to specify some initial values for the hidden states. And very often, I mean, these initial values could be fixed, but very often they're also learned. So they can also be learnable parameters. And in these state space models, an error that you see at this time can be used to influence derivatives way back when. And these will influence your learning of the network. So how do we train this network? We see how the network operates, but how do we train it? We're going to train it for an algorithm called backpropagation through time, and you'll see shortly why it's called that. Here, the training data consists of, it's a time series model. So I'm going to consider this model, this one-to-one, this simple synchronous model where corresponding to each input, there's an output. Because as I said, we will try to reduce other models to this format in order to enable the math. So here we are analyzing an entire sequence of inputs, and generating an entire sequence of outputs. So each training instance consists of a sequence of inputs. It will result in the generation of a sequence of outputs, and corresponding to the sequence of outputs, there's also going to be a desired sequence of outputs. It's the divergence between the actual sequence of outputs and the desired sequence of outputs that we're going to try to minimize. This clear to everybody? What we're doing here? So yes, no, guys. All right, so that's what we will do. Again, so as always, there's a forward pass and a backward pass. And so the forward pass is this computation. This is, it's almost like you're unrolling the network across time. So you can view this as just a giant shared parameter neural network, as we saw, where all columns are identical and share parameters. And this is going to affect our learning. And network parameters are trained via gradient descent or its variance using shared parameter gradient descent rules. We're going to be aware that the weights on this edge are the same as the weights on this edge, for instance, or that the weights of this edge are the same as the weights of this edge. Gradient computation for gradient descent requires a forward pass, and then back propagation and pooling of gradients for parameter sharing. So how does we'll hang on to the thought, Shubhe. We'll get to that, right? So how does the forward pass happen? For the forward pass, you pass the entire data sequence through the network and generate outputs. Here's a pseudocode. You're going to go through time, and at each time, the 0th layer is just the input at that time. Then you go through the layers, and at each layer, you're computing an affine function of the hidden state at that time at the lower layer and the hidden state in the same layer at the previous time. And then you put that through an activation, typically a tanh, and we'll see why. And then for the final output layer, of course, you just have an affine function of the hidden state at the final layer, and then you put that through an activation. So that's a very simple pseudocode for how the forward pass is performed. If you had a more complex network, this would be the exact pseudocode here is going to follow the architecture of the network. Here I'm just assuming a network of this kind. Okay. So is this clear to you guys? What's happening here? Yes, no? Okay. Now, when we compute derivatives, we want to compute the way we saw we would compute derivatives is to start at the very end of the network and propagate errors backwards. The very end of the network is right here, at the very end of the input, at the end of time. So now the derivatives will have to start from here and go backwards. And in going backwards, they're not merely going backwards through the network, they're going backwards through time. And so this algorithm is called back propagation through time because you're going backward through time. Now, how does this happen, right? I'm going to use this network, assuming there's just one hidden layer, but the math will generalize. And I'm going to show you how derivatives are computed for one training instance. And instead of drawing the network like so, with edges going from the middle of the box, I'm going to redraw it in this manner, just to indicate that the output of this box is actually going in as an input to this box. Okay, is this illustration making sense to you guys? That this is the same as this one here? Yes, no? Okay. And so what we want to do is to compute the divergence between the sequence of outputs produced by the network and the desired sequence of outputs. Now, the thing to remember is that this is not necessarily just the error between the first output and the corresponding desired output, the second output and the corresponding desired output here, and so on. The error may not be so complex, so simple, right? So Daniel, I will get that. I'll ask the question at the end of the class, right? So it can be much more complex. For example, if you're performing speech recognition, the network may just say hello world, right, as its output. But your actual, and especially, in the early portions of the training, the model is going to be rubbish. It can generate any odd thing. Your actual output might be an entire poem with 500 words. How do you compute an error between the two? What is that? There is no one-to-one correspondence between the output and the desired output, right? And so this is not merely a sum of the divergences at individual times. It's actually a divergence between a sequence and a sequence, and this may not be decomposable to the divergences at individual times. Is that making sense to you guys? Yes, no? What about the rest of you? That makes sense. Okay. Nonetheless, for the whole thing to work, we are going to need to be able to compute the derivative of this divergence with respect to the individual outputs. And that ends up being a bit of a challenge, right? So let's see how the back propagation works. I'm going to add some notation over here. Y of t is the output at time t. And I'm going to be using both vector and scalar notations in my slides, but we'll focus on the vector notation. So Z2 of t is the affine value at the second layer, which is the output layer in my network at time t. Z1 is the affine value at the first, right here at the first layer. And the parameters are W1 are the current weights in the first layer, W2 are the current weights in the second layer, and W11 are the recurrent weights. So this is just for notation, right? So if you can't decompose, no, that's not what it means, Daniel. It just means that the neurons all work together, but whatever they generated doesn't match what you want. That's it. And we'll see how this affects your training in next week, right?
I have a question.
So,
sir.
yes.
So back to the divergence. The main idea about divergence is that is actually the divergence between the desired sequence, like the target sequence and the hypothesis sequence. But like
Correct.
since that is sort of like intractable, like like it's not necessarily intractable, but it's the intractable computed derivative of that. So in practice, like we just like assume that's equivalent to like the basically like the sum of the divergences between the target sequence and hypothesis sequence at each time step.
We will try to drag it down to that, as you will see. Yes. Okay, so now nonetheless, the divergence, we need to be able to compute the derivative of the divergence with respect to each of the outputs. I'm going to assume that we know how to do that. And again, observe that the divergence is a function of all the outputs, right? So we need to compute this, and how we compute this can be a source of significant difficulty. We'll see the solution to some of that in the next weeks. We're going to use two rules. The first rule is this guy. If y minus 1 influences z1, if this y influences z through a weight w, and the zi influences, if yi minus 1 influences zi through w, and zi influences yi through some function whose Jacobian is written here, and if yi finally influences the loss, then given the derivative of the loss with respect to yi, the derivative of the loss with respect to zi, we've seen this in the previous classes, is simply obtained by multiplying the derivative of the loss with respect to yi, right multiplying it by this Jacobian. Do you guys remember this equation over here? Yes, no? Okay, similarly, if I have the derivative of the loss with respect to zi, how do I get the derivative of the loss with respect to yi minus 1? What would I do? Anyone remember that? Times w, because that's the derivative out here. So you just multiply it by w, right? And finally, if I want to get the derivative of w, then all I need to do is with respect to I multiply i minus 1 with by the derivative of the loss with respect to zi. This was the one-off formula that we saw in the earlier classes. Similarly, if yi influences both zi and zi plus 1, and both of them influence the loss, then the derivative of the loss with respect to yi is going to be summed over both. It's the derivative of the loss with respect to zi times w1 plus the derivative of the loss with respect to zi plus 1 times w2. You guys remember this? Over here? Right? Easy. Okay. And so we're going to use these two formula. Okay? Very simple. Here is the entire computation. I'm going to assume that the derivative, we have the derivative of the divergence with respect to each of the y's. Often we'll sort of simplify it to a situation where this divergence is the sum of divergences at individual times, in which case that derivative is simply going to be the derivative of the divergence at that given time with respect to yt. Regardless, I'm going to assume that I have the derivative of the divergence with respect to any of these y's. So, is this making sense, what I'm saying here? That we have this. Is this assumption making sense to you guys? Okay, right. So let's assume I have that, okay? Then how does backpropagation work? First, I have the derivative of the divergence with respect to yt, right? This is given. So if I want to get the derivative of the divergence with respect to the z over here, which is z2 of t, all I have to do is to multiply this guy by the Jacobian of this activation. You with me? Yes? No? Okay. So this is easy, right? And now, next step. I have the derivative of the divergence with respect to the z2. How would I compute the derivative of the divergence with respect to this element here, which is h? I have the derivative here. How do I compute the derivative with respect to this guy? So this h influences z through a weight matrix, right? And I have the derivative of the divergence with respect to z. So what is the derivative of the divergence with respect to h using the formula that we just saw? Anyone? Okay.
Sir?
Right, multiply by the weight. Right, multiply by the weight, right? Exactly. So that's all we need to do. So if I want to go down here, I want the derivative of the divergence with respect to h of t. I just multiply the derivative of z by the weight of this connection. So far, so good. Now I want to go back and compute the derivative with respect to this guy. What would I do? I want to compute the derivative with respect to this one. What would I do? Right here. No, that's going to be, so first, let me go here, right? This is going to be multiplying the derivative out here by the Jacobian of this activation, right? Do you remember this? Yes or no? Okay, so that's easy, right? And then we have this one. What is the derivative for this weight matrix? The derivative for this weight matrix is simply going to be the h over here times the derivative for the z over here, using the formula that we saw earlier. Is this making sense to you guys? Yes, no? Okay. And same thing, I can now compute the derivative with respect for these weights as the x times the derivative for z. So this first column is taken care of. Then things get a little interesting. I can compute the derivatives for these weights as the h value at the previous time times the derivative of this z, because that's what these two, this edge connects. That making sense? Yes or no? For this one? What about the rest of you guys? I have one yes. Right. So because this one has this as the input and this as the output, right? So that's what we're going to do. So we've gone through one entire column. Then when we go to the next column, again, I'm going to start off by assuming that I have the derivative of the divergence with respect to yt minus 1. I can propagate that to get the derivative for z2 by simply right multiplying this guy, which is the derivative out here, by the Jacobian for this activation. So this I've got. This is clear. And then having done that, I can move down and compute the derivative for this h over here by right multiplying the derivative here by the weight matrix. So this is easy. And so are you guys with me so far?
Excuse me, may I ask a question?
Yeah.
So the way you get the derivative of divergence with respect to the hidden state at t minus 1 is that it's the is it the derivative of the divergence?
So I'm not telling you how we obtain this derivative just yet. Let's just assume that you have it. That's the one assumption we're making. Okay? I'm just looking at the rest of the derivatives. So now, when I want to compute the derivative for this weight over here, the derivative for this weight on this edge, this guy is going to be this variable times the derivative over here, which is this term. But then I know that this edge is the same weight as this edge. So the derivative I got computed over here is going to get added to the derivative out here to give me the overall derivative for this weight. That makes sense? Why we are doing the summation here? Yes or no, guys? Okay, guys, do respond. I'll run out of time otherwise. Okay. And so here's actually wait. So if I want the derivative, that's this one here. If I want the derivative for this h actually goes up here and also goes out here. So the derivative of the divergence with respect to this h is going to be the derivative of this z times this weight plus the derivative for this z times this weight. And so that's where these two terms come in. This is the derivative for this h, which is summed over two connections. Is this making sense? Here? So we did two things. First, we showed that because I have this recurrence, at the recurrent connections, you actually have a summation of derivatives. But we also showed that for the weights, when you compute the derivatives, when you take a step back, you're actually just incrementing it with the local derivative. So now this derivative here, I can go back here, compute a derivative here by just multiplying the derivative of h with respect to this Jacobian. But then when I go down here, this derivative for this weight is going to be the local derivative, which is xt minus 1 times the derivative for the z. But that is going to be added to the derivative I computed at this time because these two weights have this edges have the same weight. And so also when I want to compute the derivative for this edge, it's going to be this hidden variable times the derivative out here. But then that derivative is going to be added to what I already computed out here because these two edges have the same weight. So for going backwards, I keep incrementing these derivatives. That makes sense to you guys? What we just saw? Yes or no? Yeah.
Is it because like perturbing like the weight, say, from the previous hidden state to the current hidden state, like for example that weight, like perturbing that weight will like basically be able to like perturb the hidden state's all time steps?
Pretty much, yeah. Right, so because perturbing the weight over here means you're also perturbing the weight out here, right? And so you keep adding those derivatives over. And so you can continue computing derivatives backward right until the very beginning of time. So I have the entire pseudocode over here. You'd compute the first column of derivatives, and then at each derivative time, you're going to be computing the derivative locally over here by just multiplying a Jacobian. then the derivative with respect to h is summing over the upward path and the recurrent path. And then the derivative with respect to z is simply computing the multiplying by the Jacobian. And for the weights, at each edge, you multiply the variable at the input to the edge by the derivative at the output, but then you keep incrementing these derivatives because every column is identical to every other column. And if you so wish, you can also compute derivative with respect to h minus 1, right? So I have pseudocode for it. I'm going to skip this. This can be generalized to any architecture. I don't have run out of time for polls, guys. I've been too slow. So I'm going to skip these 2 polls and we'll just continue with our lecture. So far we've assumed that recurrence is strictly left to right. But then if something at time t influences something at time t plus 1, and this in turn influences something at time t plus 2, then looking at this guy tells me something about this one here, right? So if I'm going to be making predictions out here, it makes sense to look both here and here, which means I want to put an arrow back this way. If I have, in things like when I'm analyzing text, I have both the present and the future, right? And so because I have both the present and the future, I could be looking at both the current time and future time to make a prediction at any time. And but then why would a network of this kind not make sense? Anyone? Why would a network of this kind not make sense? It becomes cyclic, right? You can't have cycles. And so you have bidirectional networks which break this loop. What they do is they have separate hidden states. Guys, I'll go over by a couple of minutes. Please bear with me. One hidden state recurses from the beginning of time to the end. It has an h minus 1 defined. The other recurses from the end of time back to the beginning. And so you have an initial state defined for the end. And the outputs of these two are concatenated to form the final hidden output of this block. So the overall block computes both the influence of the past and the future. This makes sense? And there's no cycle. Is this making sense, guys? I see one here. Okay, and so how do you actually perform the computation when the input comes in? The left to right recurrent state analyzes the inputs this way. The backward net analyzes inputs this way. Both their outputs are concatenated to give you the final output of the block. And these blocks can be arranged just like regular layers in a recurrent network. Is this making sense to all of you guys? How do you use the backward block? Simple, right? This is only for problems where you have access to the future, where the entire input is available to compute the output. For example, when you're performing speech recognition, you have the entire speech recording, right? Or if I'm performing part of speech classification, tagging, you have the entire sentence. And then you're tagging every word. That answer you, right? So here's a question. A day trader on a stock exchange. Exactly, Shrikant. And day trader in the stock exchange uses RNNs to make predictions from historical market data. False, right? Okay, because he doesn't have the future. Now, how do you train this network? Training is easy, right? In the forward pass within each layer, you're going to go left to right here, right to left here. You concatenate their outputs. Now, in the backward pass, I'm going to assume that going down, I have computed the derivatives at all of these places. But out here, this variable was actually a concatenation of the output produced by the forward layer and the output produced by the backward layer. So when I'm coming backwards, I'll have derivatives with respect to both HF and HB. So that means I can actually just separate the derivative with respect to the output of the block. into the derivative for the forward block, which I passed down to the forward net, and the derivative for the backward block, which I passed down to the backward net. And in the forward net, I'd be performing back propagation using these guys going back. In the backward net, I'd be performing back propagation, but it's back propagation in terms of computation. And in the backward net, you started at the end and went to the beginning. So the derivatives are going from the beginning to the end. And both of them are also going to compute derivatives with respect to the inputs of these green boxes. And because the same x is going to both, those derivatives will get added up to give you the derivative for these x's. I sort of flew through this, but did this make sense to you guys? Right. There's no, the forward and backward nets within the block can be computed in parallel, right? So you can compute them in, so you can perform the back first and the forward, I mean, because they're independent computations, their outputs are concatenated. That answer, Shive? Okay. And so that's it. And then back propagation happens as before. I have pseudocode for it. I'm going to skip that. What I am going to do is to go back to poll 3 and see if I can get you guys to answer poll 3, because if I can find it somewhere here. And that pretty much, okay. SGD trains neural networks one input at a time rather than over batches of inputs. The corresponding equivalent for RNNs would be to update the network after each input vector, true or false. What do you think? I see one answer. False, because you have to analyze the entire sequence of inputs, right? In RNNs, the divergence we minimize as the sum of divergences for individual inputs, true or false. Okay, if the divergence is the divergence between the actual sequence of outputs and the desired sequence of outputs, true or false. This last one, true. Beautiful. So although I sort of rushed through the lecture, I think you guys got most of it. And so the story so far, time series analyses must consider past inputs along with the current input. Recurrent networks look into the infinite past to a state space network. To train recurrent networks, you have to define a divergence between the actual and desired output sequences. And back-propagating gradients over the entire chain of recursion must be performed. It requires back-propagation through time. You pool gradients with respect to individual parameters over time. Bidirectional networks analyze data both beginning to end and end to beginning within each block. And these networks, back-prop must follow the chain of recursion separately in the forward and backward nets. That's it. I thank you for bearing with me the 2 extra minutes. I can take some questions. By the way, so RNNs are great models for time series prediction, classification, sequence generation, but they have all kinds of problems, and we'll deal with them in the next class. Before I take questions, I'm going to stop the recording.